So the assignment number 4, we are approximating a function using MLP, multi-layer perceptron. So the function that I've used here is sin x plus cos y, and the variables x and y goes from -4 to 4. So for this approximation, I've used 100 points of both initially. So we calculate the actual function value at these 100 points of x and y. And the structure of our MLP for function approximation is 2 hyphen 80 hyphen 1. So this 80 are the hidden layer neurons, and this 1 over corresponds to the output layer neuron. So W1 here, the hidden layers are 80. The W1 corresponds to random weights that we assigned to the first layer initially. So the first layer will have hidden layers cross 2, that is 80 cross 2 weights, and the W2 corresponds to weight layers in the output layer, which is 1 cross 80. So B1 corresponds to the bias with respect to the hidden layer neurons, and B2 is the bias corresponding to the output layer neuron. So maximum iteration for this I have kept as 60. So initially W1, W2, B1, B2 would be random, and then we will move into an iterative loop over number of iterations, and we will use an update mechanism or update rule known as backpropagation algorithm to update the same. So here we have this W2, B2, W1, B1 will be updated over the iterations every time. So this iteration and this update is based on backpropagation, that from the output layer to the input layer we are backpropagating, and we are calculating based on the A1 that is the output. I mean 10 as W1, and the output of function MLP is W2, I mean weight in the output layer into A1 plus B2. So this A1 is the output from the first layer. So we go into the iterative loop. So initialize, we have to initialize this W underscore 1, W underscore 2 to B1, B underscore 1, B underscore 2. And this ES is error, mean square error. We have to initialize and set them to 0 over every iteration. So then we run an iterative loop for the length of X and for length of Y, such that we are calculating this function value over 100 cross 100 points, X and Y, 100 cross 100 points. So the error would be desired. Desired is the actual function that we have, sin x plus cos y, minus the function, approximated function given by MLP using this formula. So initially W1, B1, W2, B2, all were random weights for the first iteration I'm talking. So this one are the random initially. So how to update them? So here we have assigned W underscore 2 as 0 initially, and then we will take a sum of after updating, so over the all the points. So that sum will be averaged over these points, 100 plus 100 points, and then we will store update the W1 matrix using this particular formula, that update W1 old plus the averaged W underscore 1, which we have got with this update mechanism over 100 plus 100 points. Same goes with mean square error. Same goes with W2, B1, and B2. So after certain iterations, our MLP will be trained, the neural network will be trained, and we will get the final values of W1, W2, B1, B2. So these values can be used further to check what is our mean square error if we give some random points to the neural network. So the second part would be giving some random points which are not part of this X and Y vectors, and we have to see what would be the mean square error after learning and after approximating the function. So we'll first see how the approximation is done over certain iterations. So our max iteration is 60. Now I'll run the program. So here we see that our function is also changing. Mean square error over different iterations are here, X, Y approximated function, and here also we can see the displayed values. So over iterations, our mean square error value is decreasing, which means it is giving us a better approximation over the increasing iterations. The surface of the approximate function is also changing. So yeah, after 60 odd iterations, we have got our approximated function surface like this. And the original surface of sin x plus cos y is like this, from -4 to 4, and here from -4 to 4. So we have closely approximated it, but we have an error of zero point 0.3, mean square error of zero point 0.3. So there can be a much better approximation if we increase the iterations or we increase the neurons. And also we want to further approximate it on a high end. We can use different mechanism like T-plan, trigonometric functional artificial neural network. So we can use that. So we'll see how our over the iteration, how our mean square error changed. So initially our mean square error was above 600, and over iteration clearly went close to zero. Here is close to zero. So this can be seen that our W1, W2 metrics have adjusted to reduce the mean square error. So now we will look at another function file, which is a testing function file, which will give an input as W1, W2, the learned W1, W2, B1, B2, X and Y, and the output would be the mean square error of the test xt is the test x variables or test y variables and the function test. So that would be our output. Now we look at the test file. So here we have to take some 40 random points which are not part of the training. So we can do that using this simple formula, creating 200 random points between the range of -4 to 4. So we'll see what are those points. So this XX has 200 points. So this has 200 points which are in the range from -4 to 4. And same goes with y, y also. But now we have to check that if these points are also the part of training point or not. So for that we again run a iterative for loop such that if a particular element in that is a member of the x is the original x variables, vector of variables that we used for our learning. So if that is a member, then we don't use that for training, testing. If it's not a member, so we'll use it for training. So there will be many points out of 200 which will be part, which are not part of the training and are distinct. So we'll take the 40 of them. So this xt corresponds to some 40 points which are not part of the training. These are some 40 distinct. Same goes for yt also. And now we will evaluate the function, the actual function using this, and then again using this w1, the learned w1, w2, b1, we will use calculate the approximate function of MLP. We will calculate the error, the desired minus the approximated. We will square it. We will average it. We will sum it and average it over all the points. That is z. So z would be for here. It would be, since we are taking 40 cross 40, I guess. So it will be 1600, 40 cross 40. So the mean square error will be 0.3273, and this graph shows. So these are the points which were used to approximate this function, the surfaces of sin x plus cos y. So these points were used to approximate the particular function shown in the graph, and the mean square error upon doing the same is 0.3273. Yeah, thank you. So further, if you can increase the iterations to 100 or what, so this value can again go below. And as I mentioned, increasing neurons also will give us the good approximation. But the question the question states that we have to use minimum number of neurons. So I've kept 80 over here. And doing the procedure after 60 iterations, we are getting a mean square error of 0.31.